Hey guys, welcome to video number 22. Today we're going to start talking about resonance circuits, and we'll begin with an examination of the series resonance circuit. Alright, so we've got here a sinusoidal voltage driving a resistor, inductor, and capacitor in series. We define the resonant frequency as the frequency where X sub L and X sub C cancel out, and we'll designate that as F sub O. All right, if we look at the graphs of X sub L and X sub C versus frequency, the resonant frequency occurs where these two graphs intersect. That's F sub O, and we can figure out what that value is by setting X sub C equal to X sub L and solving the resulting equation. All right, I'm going to do that now. It's pretty straightforward. And I'm going to start by multiplying both sides by the denominator 2 pi FOC, and that gives me 1 equals 4 pi squared FO squared times L times C. All right, we want to get frequency by itself, so let's divide both sides by 4 pi squared LC, which gives us 1 over 4 pi squared L times C equals FO squared. And we take the square root of both sides. We end up with F sub O equals 1 over 2 pi times the square root of L times C. All right, anyone that's involved in electronics, either as a hobby or professionally, should be intimately familiar with this equation. It's very important. And because of that, I made a nice, pretty looking typeset version of it that I'll drag over so that you'll have an aesthetically pleasing screen to capture if you'd like to, make reference of this. All right, so here we go. There is our frequency, resonant frequency expression for this circuit. And before we go on talking about that, let's drop back in time a little bit and look at the homework problem I left at the end of the last video. If you recall, we had a 10 volt sine wave at a frequency of 1 kilohertz driving this series RLC circuit with 1K, 47 millihenries, and 0.1 microfarads. Right, we figured out all of the phasor equivalent values for this circuit, and your job at the end of the last video was to determine this current. All right, we know that I is equal to Vn over Z, where Z is the total impedance of the circuit being driven, and that's R plus XL plus XC. All right, writing those down, we had 1,000 ohms plus 295J for the inductor, negative 1,600J for the capacitor. Combining and simplifying the imaginary part, we get 1,000 minus 1,305J ohms. And then converting that into polar form, we get 10 volts at 0 degrees divided by 1644 at negative 52.5 degrees ohms, which gives us a current of 6.1 milliamps at 52.5 degrees. That just means that the current entering this circuit is leading the voltage by 52.5 degrees. All right, now, that's all well and good, but suppose we want to figure out what happens in this circuit when it's in resonance. Well, let's go down to the next slide, and we'll tackle that problem. All right, so for the circuit in resonance, we know FO equals 2 pi times the square root of LC. So let's pull up our handy Microsoft calculator and evaluate this equation. We've got, let's see, L is 0.047 henries times 0.1 times 10 to the negative 6th power farads. We'll take the square root of that product, times 2 times pi, and then the reciprocal. And we get a frequency of about 2,322 hertz. 2322. All right, so we've got our resonant frequency. And now let's figure out what X sub L and X sub C are. Remember, they're equal at this frequency, so we'll just find X sub L. That's easier, right? We know X sub C equals X sub L equals 2 pi FO times L. So what does that give us? Let's call up our calculator again. And we've got 2 times pi times 2322 times 0.047 henries gives us an X sub L of about 686 ohms. And we know X sub C will be the same. We could verify that, but I'm not going to bother going through the calculation on here. You can do that yourself. And now let's figure out what the current is, okay? So I is equal to V over Z. So that's going to be 10 at 0 degrees volts divided by, well, I'm going to write it out, and we'll see how it all shakes out. Here we've got 1 at 0 degrees K ohms plus 686 at 90 degrees ohms plus 686 at negative 90 degrees ohms. And these two just cancel, so our current is 10 volts at 0 degrees divided by 1 at 0 degrees K ohms, which equals 10 at 0 degrees milliamps. So there's our current. It's 10 milliamps at 0 degrees. All right, let's clear the boards here a bit, make a little bit of room. And now I'm going to determine the voltage drops across each of these components. Let's start with the resistor. All right, that's V1. And we've got V1 equals I times R1, which is 10 at 0 degrees milliamps times 1 at 0 degrees K ohms, which equals 10 at 0 degrees volts. Okay, now let's think about this for a second. I'm applying 10 volts at 0 degrees, and the drop across this resistor is 10 volts at 0 degrees. And at first glance, it seems like, well, then these voltages must be 0, but they can't be because these reactances aren't 0, and they've got current flowing through them. So let's figure out what voltages we do get across the inductor and capacitor. All right, so starting with V2, we have V2 equals I times X sub L, which equals 10 at 0 degrees milliamps times 686 at 90 degrees ohms, and that gives us 6.86 at 90 degrees volts. All right, so that's the voltage drop across the inductor. The voltage drop across the capacitor, V3, is equal to 10 at 0 degrees milliamps times 686 at negative 90 degrees ohms, which equals 6.86 at negative 90 degrees volts. All right, so there are our three voltages. We've got 10 volts here at 0 degrees. That's the drop on the resistor. The drop across the inductor, 6.86 at 90 degrees, and the drop across the cap, 6.86 at negative 90 degrees. All right, kind of an interesting result. We've got the entire voltage dropped across the resistor, plus voltages dropped across the inductor and the cap. But because the phasors work out to cancel these two, everything is consistent with Kirchhoff's voltage law. Right? The sum of the voltage drops here equals the applied voltage, and when we add them, that's exactly what we get. Pretty cool. All right, now let's leave with a homework problem again. And this time I'd like you guys to figure out what capacitor value C1 has to have in order to produce a resonant frequency of 10 kilohertz for this circuit. Then at the resonant frequency, what do we have for X sub C and X sub L? All right, and I'll leave you with that. And the next time we'll look at parallel resonance circuits. So I will talk to you then.